Hi, everybody. Welcome to the next session. We have already done a few of these sessions, but this is the session which is dealing with the unpacking of the problems that were set by the South African Mathematics Foundation in 2024. And this particular competition is the junior competition round 3, which has 15 questions. And we are grateful to the South African Maths Foundation, SAMF, www.samf.ac.za, for their hosting these sessions. All right, so we are going to go straight into the paper which was set in 2024, the junior round 3. All right, so let's just... Okay, so you can see the screen, hopefully. And we go on to the very first question. Okay, the first question says the Old Mutual Maths 24 game was played in schools countrywide many years ago. All right, so there was a game which is like this. What it says is that the aim of the game is to get an answer 24 through mathematical manipulation of the numbers on the card. You can only add, subtract, multiply, and divide. You must use all 4 single-digit numbers. They actually mean these 4 numbers, all 4 numbers on the card. I think actually this should be removed. All 4 numbers on the card exactly once to achieve a total of 24. So you can add, subtract, multiply, and divide or whatever. Like for instance, if I want to say, I want to get a whole number, so 8 times 3/8 will be a nice number. 8 times 3/8. Okay. So that takes care of these two. That gives you 3. And then times 2. Say 8 times 3. 3/8 is 3. 3 times 2 is 6. And then I can get 24 by dividing this whole thing by the 4th number. Okay, so you're using all 4 numbers here, and the answer is 24. So the first guess I took is the correct one. But you can try various things normally. You try out various possibilities until you come to 24. Okay, let's get on to the next problem. All right, so this is question 2. In the 3 by 3 grid below, each of the integers 1 to 9 are placed in such a way that the products of the rows and columns are as shown on the diagram. So you're going to place the numbers 1 to 9 here. So the product of these 3 numbers is 15, those 3 is 224, and so on. Just one moment, please. So when we multiply these numbers, these 3 numbers, you are going to get the numbers which are on the side. All right, now one important thing is to notice, suppose I take a number like this. Take a number like this. This number is a factor of 224 because when you multiply this and two others, you get to this. So this number is a factor of 224, and it's also a factor of 126. So you are looking for a common factor of 224 and 126 to slot in here. Okay, so if you look at all these pairs, you see in one case, there's only one possible answer, and that is when, like a 224 and 126, there are many common factors. It's 2 and 7 also goes into both of them and so on. And if you look at many of these pairs, there are lots of common factors. But in one case, there's only one common factor, and that is in the case of the 15 and the 40. The common factor is 5. So that has to be 5. Okay, so these two numbers when multiplied gives you 15. So this product is 3. I can put down 1 times 3. All right, so that takes care of that. Now the next one is, I mentioned this particular square here because this is 7 times 32, and this is 7 times 18. So what can go in here is 7, or another common factor is, okay, you could also have 2. 2 is a common factor. It goes to this and that, and those are the only two common factors for 32 and 18. Is that there's also 14, but you're only putting the numbers from 1 to 9. So this is either 7 or 2. Now, suppose this is 2. Then you got 3 times 2 is 6. And you got too much here. This would be 21. That wouldn't work. So you have to put 7 here because 3 times 7 is 21. And the other factor is 6, which is one of the numbers here. So let's put 7 here. You can't put 2 because then this number becomes too big. So you got 7. 3 times 7 is 21. 21 times 6. All right. Now if you look at these two, they multiplied to 8. 5 times 8 is 14. So this is a factor of 8. And this way, you got these two numbers multiplied to get 32. So this is a factor of 32 as well. So there are quite a few factors for 32 and 8. So you could have 2 or 4 or 8. 8 is a factor of 40, 8 is a factor of 32 as well. Okay, now if it was 2, 7 times 2 is 14, and that gives you, the other number is too big. If I take out the 2 from here, I get the remaining 6. So that is out. So I get a number which is more than 9. So this could be 4 or 8. Now, if I put 8 here, then I get 5 8 is 40, and I'm going to have a 1 here. That's repeated. So I can't put an 8 here. Because if I put an 8 here, 5 times 8 is 40, and this is 1. I'm not allowed to do that. So we can eliminate 8. So the only answer is 4. So the only number that goes in here is 4. And after that, this is easier. So 5 times 4 is 20, and you have to put 2 here. 6 2 is 8. I'm going to put a 9 here. 1 times 9. And you can see all the 9 numbers are repeated. Okay, so once you've got a few, you can get all the others because you know that the product of the numbers you know the product of all the numbers. So that's the answer to that question. And I've got all the answers also in this thing. Let's just check to see. So if you notice, 153847926, and that's what I had before. Okay, so this is the answer. Right, let's get on to the next problem. And the next problem is question 3. Now, question 3 says the square has got a red square, a yellow, and a blue. The blue square is, the red square has got area 16. What's a square? So if the area is 16, then this has to be 4 here. And this also has to be 4. Okay. And a yellow square. The blue square has got area 64. So I've got an 8 here. And I've got an 8 here. It's a square, so the side must be 8 times 8. The gray area is 232. Now this is not a square, but it's a rather awkward looking figure. But we must try to break it down into smaller units so that the sum of the areas is 232. So how do you find the area of this? I'll have to complete the rectangle. So the gray area is the sum of these 3 rectangles. So, and that'll give me an equation because we know the answer is 32. Now, where do we start? We don't know the area of the yellow square. You're asked to calculate the area of the yellow square. So let's call this x. So I need to calculate what is x squared. X and, of course, x squared is what I need. That's the area. Okay, now, this side here now is 12 plus x, the side of the large square. Is x plus 12, right? Where x is the side of the yellow square, which you can see. Okay, now let's work out all the other dimensions. So if the side is x plus 12, what must I add to 4 to get x plus 12? It must be x plus 8. Okay, so I got that. And this is 4 here. And this is x here. And this is 8 here. The only thing I don't have is this. But it's x plus 12 is the side of the large square. So this has to be x plus 4. But when you add these two, you get x plus 12. Okay, so now we've got all the dimensions. So we can work out the areas of these various things. Like here, the rectangle is got side x and 4 and x plus 8. And the area for this is 4x plus 32. The area for that one. This is x here. I don't know what the side here is. So let's just hold on with that. But this one, yeah, I've got 8 and x plus 4. That's 8x plus 32. Now, what is this equal to? Okay, so this is x here then. This part here, this is a yellow square. So this is x here. And the whole thing is x plus 12. So this has to be 12. Right? So we just use the fact that this part here is x. So now you've got the area for this is 12x. All right. So if you work out the 3 areas, let me just take this 12 out here. That's in the way. If you work out the 12 areas. And the 3 areas, when you add them up, the answer is 232. So when you add up these, 4x plus 12x plus 8x, that gives you 24x. I'm adding in the gray area. And you got 32 plus 32 is 64. And that gives you 232. So you got an equation involving x. And if you bring the x's to one side, 24x is equal to, when you take this to the other side, you get 168, because 168 plus 64 is 232. Well, x is a nice whole number, 7. And the area that you're looking for is x squared, which is 49. Okay, so that's the solution to that problem. Let's get on to the next one. Just to check to see whether my answer is right, because I've done all these problems. And so you can see the area is 49. Okay, so let's get on to question 4. Question 4 says an Egyptian fraction is a finite sum of distinct unit fractions. A unit fraction is a fraction with numerator 1. All right, so an Egyptian fraction is a finite sum of distinct unit fractions. So write this as Egyptian fractions in 2 different ways. So what have I got? I've got 20. I want to write it as an Egyptian fraction. An Egyptian fraction is a sum of unit fractions, and unit fraction has got denominator 1. So it's a sum of a fraction like this. We don't know how many there are. Right. Okay, but if you say if it's a sum of only 2 such fractions, then you will have the 20 over 24 is equal to 1 over a1 plus 1 over a2. And that is equal to common denominator a1, a2. Yeah, it's a1 plus a2. Okay, so you can take a1, a2 to be 24. And you'll see that a1 is a factor of 24 because you've got a1, a2. a2 is also a factor of this. So if you think about this, if you write this as and suppose I call this x1 plus x2 plus x3 and so on. And now you have that x1, if it's a factor of 24, then the x1s cancel and you'll have a 1 at the top over something. The same thing if x2 is a factor, you'll have x2 will cancel off with this factor at the bottom. You'll have 1 over something plus 1 over something. So in other words, what I'm looking for is need to find factors of 24. But you want them to add up to 20 because I got 20 at the bottom. That sum to 20. Or add up to 20. Right. Okay, so the next thing to do is to find what the factors of 24 are, and we'll look for factors which add up to 20. Okay, so let's first find what the factors of 24 are. Factors of 24. It's 1 times 24, 2 times 12, 3 times 8, 4 times 6. And that's it. After this, you're going to have 6 times 4, which is repeated. All right, now we need to work out, see which numbers add up to 20 here. Now, let's try. You can take 6. The other one is 14. No. 4 and 16. No. 8 and 12. Okay, 8 plus 12. We've got 1 so far. And you'll have 3 plus 17. No. 12 plus 8 I've got. 2 plus 22. 24. Okay. This is the only one that I've got. 8 plus 12. And then, if I look for 3 numbers, now 8 I can write it as 2 plus 6. And both of them are here. So I can put on 2 plus 6 plus 12. Okay, and 12, I can write it as 4 plus 8. But they are distinct, you see, so I can't have 4 plus 8. I can't have 3 plus 9, I can't have 2 plus 10, and so on. Okay, so that's it. And but you can see 6 is 2 plus 4. Oh, that's no good. Yeah, 12 is 4 plus 8. So I could have written this as 2 plus 6 plus 4 plus 8 also. Right. So they say in 3 different ways. I've got 3 different compositions, decompositions you call them, for 20. And therefore 20 over 24. If I put 8 plus 12 over 24, that gives you 1/3. 12 over 24 is half. 2, 6, 12. All over 24. 2 over 24 is 1/12. 6 over 24 is a quarter. And 12 over 24 is a half. And here, the same thing. 2 over 24 is 1/12. Plus quarter, plus 1/6, plus 1/3. So these are the 3 different ways in which these are the 3 Egyptian fractions, right? Which gives you the sum of 20 over 24. All right, so the interesting thing here is that if you put the denominator here, the numerators will have to be factors of 24 for it to become unit fractions like this. So that helped a great deal to make that observation. Okay, so let's just get on to the next problem, which is question 5. Okay, I've got the question 5 right in the corner. Now this looks like a rather complicated one. 8 towns are connected to the map shown. So where's the map? There's no real map here, but anyway, there's something like it. I think it's this one here. So these are the 8 towns. They got all these funny names. These are all towns in England, evidently. Bromley and Hampton and so on. But I noticed the nice thing is that the initials form A, B, C, D, E, F, G, H. So that's nice. You don't have to write down the names of all these towns. You can just identify them with their initials. And more than that, instead of having this rather funny looking picture, I could put it like this. Then I have A, B, C, D, E, F, G, and there's an H here also. H, G, H, and you come back to A. All right, so you got all these towns. Now, route 1, it does this. It goes from all these things. I don't want to name all these tongue twisters. Okay, let's name them with their initials. So I got C, D, E, F, G, H, C. So C, D, let's look at this picture here. C, D, E, oh, there's an F here also. Okay. C, D, E, F, G, H, C. So G, H, G, H, C. Let's do it again. C, D, E, C, D, E, F, G, H, C. So C, D, E, F, G, H. Oh, so this is joined. All right. So there's your root one. You see, I've done it separately here, but I put a dotted line here because that dotted line was not in the picture. Okay, so that's root one. Goes right round like this. And you'll see why I'm doing this just now. And then what is root two? Root two is A, B, C, F, G, H, A. So you will see that you got A, B, C, F, G, H, A. So this is A, B, C, and you're coming down here. A, B, C, F, G, H, A, F, G, H, A. So it's whole thing here. This is your root two. So you can see I got root two put down here and I got a dotted line. Now, so I got root one is this entire thing right round. Root two is this entire thing right round. And root 3 is A, B, C, D. So root 3 is actually this entire thing. A, B, C, D, E, F, G, H, A. Right, so this is root 3. So you can see root 3 is this thing here. Now, they ask you, the question is, how many kilometers is root 4? Root 4 is C, F, G, H, C. So there it is, C, F, G, H, C. So root 4 is this part here. Now, I told you I'll come back to this. So this is root 2, and this is root 1 right round, including these dotted lines. If you add these two roots, right, you will get these three dotted lines plus that one dotted line, which gives you this thing here. Right? And that is precisely what we had for root 4, CFGHC. Right? So this is the root 4. So when you add these two, it's like adding the dark lines. If you add the dark lines, you get this, plus the dotted lines. So this thing here can be written as this dark one plus the dotted lines. But the entire thing is root 3. So you have a nice equation here which says the root 2 plus root 1, if you add these two, you're going to get root 3 plus root 4. Okay, it's just a matter of observing how you can patch and make up these roots. But we know what these roots are. Root 1 is 17 kilometers long. So this is 17. And root 2 is 12. And root 3 was 20. And we needed to work out root 4. Okay, now that's straightforward. Because 12 plus 17 is 29. So root 4 is 9 kilometers. Make sure you put the units at the end of your solution. So this was a rather tricky one. You have to think about this. And I've written out the thing in full. and you can have a look at it. I'll show it to you now. So this is exactly what I said, but everything is written out in full. And if you didn't understand what I said, you can go over, freeze it at this plane and try to work it out. Okay, question 6 says the letters of A, I, M, R, T, X can be arranged in 720 ways. Okay, yeah, the number of ways in which you can arrange n objects is n factorial. Hopefully you know that. N factorial means 1 times 2 times 3 all the way up to n. So you got 6 things here, and the number of ways in which you can arrange 6, they're all different. The 6 different things is 1 times 2 times 3 times 4 times 5 times 6, which is 6 factorial. Now, you should know that 5 factorial is 120. It's nice to know that as a fact because you got 24 times 5. So 120 times 6 is 720. So 720 is 6 factorial. All right. Now, they say you arrange all these things. For instance, this is an arrangement. These are different arrangements. Now, suppose that all the possible arrangements are listed in alphabetical order and numbered from 1 to 720. Which number would be assigned to this particular arrangement, which reads as matrix? Okay, so let's put them in alphabetical order. You've got A, I, M, R, T, X. They're already in alphabetical order. Right? R is before T, which is before X, and so on. So let's see. You're going to start with A, and you're going to write down all the possible arrangements starting with A, and there are 5 symbols here. And if you work out all the possible arrangements with A, you're going to get 5 factorial. A is front, and these 5 can be arranged in 5 factorial ways. And that's 120. Okay, so once you finish all the A's, you get to the next letter of the alphabet here. That is I. Then I too, you've got the five other letters, remaining letters. And that too can be arranged in 5 factorial ways. So the first two, you got 240 words so far. So far we have 240 words. Let me just see what's the first word, beginning with. It'll be in that order. AIMRTX, and ending with, you'll have I, and now you'll have the very last one in this. You'll have to write this in backwards now. It's XTRMIA. Right. So once you exhaust I, now you go to the next letter, which is M. Now we want to find out where is M in the slot. Well, certainly MA is fine, right? But now you've got four letters here. Okay, you have MA, and then the first one that comes here is I. Suppose you look at I here. right? Then you've got, you can start with MAI. And how many letters have you got after MAI? There are only three symbols here, the TR and the X. So that gives you 120 plus 120, 240 so far. And you got another 6 here. Because these three symbols is 3 factorial. They can be arranged in 6 different ways. So once you finish MAI, so you came to MAI, the next one is R. So you'll have MAR, and there too there are 6 symbols. So now you finish MAR, and now you come to MAT. Okay, so you got MAT, and now the very first one after that will be IRX, and then you'll have MAT. Still starting with I, you'll have IXR, and you'll have MAT. The I is finished, so you go to now R, and the first one from there is IX. Okay, so that's where we are. So you got 240 letters, words there, another 12. 252. So the last one up to this was 252. And this is the 253rd number. This is the 254th number. And the number you're looking for is the 255th number. So this is the position. Which number would you assign to this matrix? It's 255. It's just a matter of counting all the previous numbers in a systematic way. Right, so that takes care of question 6. So let's get on to the next question. Let's just check first to see whether the answer is 255. So that's fine. We are at the correct answer. So let's now get on to the next problem. Question 7. Oh, you got another complicated looking diagram here. The diagram shows a commercial wind turbine with real life dimensions. All this nonsense. But anyway, each propeller is 56 meters long. Okay, so you got a propeller. These are propellers. It's 56 meters long. It's written there. And in a wind speed of 54 kilometers per hour, the turbine turns at the rate of 15 revolutions per minute. So calculate the speed of the tip of the propeller blades. So that one. In kilometers per hour. So how do you do that? This tip here, tip completes it's 56 meters long. So it completes one complete revolution. That is 56 multiplied by 2 pi r, right? The circumference is 2 pi times the radius. So this is a revolution equals 1 revolution. Okay, it does 15 revolutions per minute. So, in other words, if it does this in one revolution, so in 1 minute, the distance traveled by the tip equals, okay, it's 15 revolutions. So it's 56 times 2 pi. That's one revolution. I'm working it out as 112 times 15. And this is in meters. So you got, because the propeller is 56 meters long. So this is in 1 minute. So you want to know how many meters it travels in 1 hour. It says speed of the propeller in kilometers per hour. So let's work it out. In 1 minute, it's that. So in 60 minutes, 1 hour, the distance traveled by the tip is 112 pi times 15. That's in 1 minute times 60. Right. So that is the distance traveled by the tip in 1 hour, and that is in meters. But you want to find out how many kilometers it travels in 1 hour. So speed in kilometers per hour is that 112 pi times 15 times 60. But you have to divide it by 1,000 because there are 1,000 meters in a kilometer. So you have to put all this over 1,000. Right. Now, let's see, we can cancel. 10 goes into this 6 times, and 10 goes into this. Cancel off one of the hundreds or the zeros. 5 goes into this 3 times. 5 goes into this 20 times. Okay, so you can still cancel the 20. 4 goes into this 5 times, and 4 goes into this 28 times. So you got a 5 at the bottom, and it doesn't cancel anymore. So you got 28 times 3 times 6 times pi, and that's 504 pi. 28 times 3 is 84, times 6 is 504 pi, divided by 5. And they say answer, leave your answer in terms of pi. So you can leave your answer like this, or otherwise you can make it 5 goes into this 100,8. When you divide this by 5, you get 100,8 pi. And this is in kilometers per second, per hour. So that's the speed of the tip. Interesting. The windscreen of 50. Okay, so that takes care of this problem. And I think I'm going to do, let's just check to see whether this is the same answer that I got. Oh, there it is, 108 kilometers per 100.8 kilometers per hour. So that is the same answer that I got. Let's do question 8. Don't worry about the figure. I've got that figure to help me along. This is the question. Determine the number of six-digit numbers that are divisible by 6 and contain 2024 in some position. So you have case 1 where you have 2024 in the first position, right? Like that. They must remain together, it says here. Or you have the second case where you have 2024 in the middle. It's a six-digit number, right? This takes care of 4. There's still 2 more to fill. And the third case is where you have the 2 are in the front. See, those are the only possibilities. You've got 2 at the end, 1 on either side, and 2 in the front. Now, what is the question? It says, determine the number of these which are divisible by 6. Okay? So you want all these numbers to be divisible by 6. Now, a number is divisible by 6 if it's divisible by 3 as well as by 2. Okay, so you want the numbers to be sorry. Sometimes the writing is so atrocious, I myself don't understand it. Okay, the numbers are divisible by 6. So therefore, they are even. It's a multiple of 2. They're even. It's also a multiple of 3. And for a number to be a multiple of 3, the digits sum. The sum of all the is a multiple of 3. Okay. So that will, if when that happens, it's a multiple of 3 and it must be even for it to be a multiple of 6. So you're looking for those even numbers which are multiples of 3. Now, at the moment now, the sum of these digits are already 8. Okay? And you want the sum, the entire sum, to be a multiple of 3. So you could have a 1. You could have had the digit sum of those 2 stars here. We've got a star here, star here. The sum of these 2 unknown numbers could be 1, could be 4 also, because you got 8 plus 4. In fact, it's 1, and you keep adding 3 to this. 4, 7, 10, 13. You can go up to 16. So you can have these 2 numbers added to 16, plus 4 is 20, plus 2 is 24, 2 plus 24. And that is a multiple of 3. Okay. But you can't go beyond 16. 19, you can't have 2 numbers adding up to 19. The last one you had is 16. And so let's just see. These are the possible sums of star and star. Now, let's have a look at what 2 digits must add up to 1. You could have 0, 1, sorry, 0, 1, or 1, 0. Right? So you could have had 0, 1, and that is a multiple of 3, or 1, 0. It's also a multiple of 3. But remember, you want to have a multiple of 6. So I'm going to just be a little bit careful. Let me just first work out in how many ways this sum here is obtained. So the sum of 4 can be obtained by 0, 4, 4, 0, or 1, 3, 3, 1, or 2, 2. That's the number of ways in which 2 numbers can be added to get 4. For 7, you can have 0, 7, 7, 0, 1, 6, sorry. You could have 1, 6, 6, 1. You could have 2, 5, 5, 2. You could have 3, 4, 4, 3. And that's it. After this, you want to come back to 5, 2. Okay, so there's so many ways of adding up to 7. And with 10, I think there's even more. You'll have 1, 9, 9, 1. 1, 8, 2, 8, 8, 2. 3, 7, 7, 3. 4, 6, 6, 4. I could have 5, 5. Okay. And 13. 13, you can't have 112, you see, because these are all single digits. So you could have, you can't have 2, 11, or you can't have 3, 10, but you can have 4, 9, 9, 4, 5, 8, 8, 5, 6, 7, 7. You can have that. And 16, the only way you can have it is 7 and 9, 9, 7. All right, so there are a lot of cases here. The full count means how many are there in each? Here you got 2. So here you got 1, 2, 3, 4, 5. Here you got 1, 2, 3, 4, 5, 6, 7, 8. For 10, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. For 13, I've got 1, 2, 3, 4, 5, 6. And 16, I got 2. Okay, so that's the full count. But now we want to only count the evens. All the numbers must be even. Okay, so let's count the even numbers. So this is even in that lot. In this lot here, you got 0, 4, 4, 0, and that. So there's 1 even here, and there are 3 evens for 4. For 7, you got 1, 2, 3, 4. So you got 4 evens for 7. And for 10, you've got that, 2, 3, 4 also. You got 4 for 10. And for 13, you got 4, that 1, 2, and these are all odd. And here, neither of them. Now, this data we need to solve the problem. Right. Maybe I should have discussed the problem first, and then you will know why we did all this. You see here, the last 2 digits, they have to be even. These must be even numbers. So you look at all the multiples of 3, which are even. Now we counted them. The multiples of 3, which are even, are this: 1 and 3, 4, 8, 12, 14. Oh, I had 7, 6 here. So this is supposed to be 3. 3 there. I didn't understand my own writing. 6 plus 7, 7 plus 6. Okay, so now you get 4, 8, 12, 15. Actually, if I remember correctly, there were 16. So I think I'm missing one here. There's some even number which I didn't count. 1, 2, 3, 4, right? And here I got 1, 2, 3, 4 again. And this I've done. That's one. Hmm. Okay. And here altogether, so there are 15 numbers in that lot. If I remember, it was 16, but I can't see where I'm missing it. Hmm. Okay, now in this case here, again, you have the even count. So there's 15 here, and there's 15 here. So it's the same kind of a situation. But except you can't start with zero. Remember, it's a six-digit number. So you have to take out all the even numbers which have got a zero in the front, right? And this is one of them. This is one of the numbers. I can't count that one. That's an even number. And let's see which ones have got zero in the front. Those, that, and that. I think those are the only numbers which have got zero in the front. And there's only one of them which is an even number. So you have to take out, right? You count everything except 0, 4, because then 0, 4 will be, you can't put a zero in the front. Okay. And here, you can put anything you like here because it's an even number. So you can put any one of all these. So 7, 15, 24, 30, 32. Oh, yeah, you got 8, 8 here as well. Hmm. You see, 8 plus 8 is also 16. So that's where that extra 1 came from. So this is really 3 here, and this is 1 here. So this is 16. Right. So this is 16, and this is 15. And I forgot to add in 8, 8. And then when you add up all this, you get 7, 15, 24, 30, 33. So there are 33 numbers of this type, 16 of that type, and 15. Oh, now again, this 33, I have to eliminate the ones which are starting with 0, and there are 3 of them that start with 0. But here you can put, it's already even. So you count every one of them, you get the full count, except those which start with 0. So if you add up all these, the answer is 31 plus 30 is 61. So there are 61 numbers which satisfy this condition. Right. I did do this thing, that is why I remember the answer, and I was able to correct myself. Okay, if you look at, I've written down the solutions for every one of them, so you can go and check it out again. And there it is, you got 61. So you can see 88. I missed that 88 in my count. All right, then the next one is question 9. You got a symbol here. It means the greatest integer less than or equal to x. So if you take a number like this, it need not be an integer. You could take a number like this, 6,96. So the greatest integer, the largest integer, which is smaller than this, is 6. So it's a kind of like rounding off. But you don't, if I round off, this would be 7. Right? Because I go to the next one, the one which is closest to. But here it says it must be less than. In other words, you lop off the decimal. So here, a -5, if you've got a negative number, then it's actually -6. You have to think about why that is so. But it says greater integer less than or equal to, so this thing here is actually equal to 4. Right, now you have an equation here. And the question is, for which values of x is this equation true? But now you've got a 2x and you've got an x, and you know what this means. So how do you solve this kind of funny looking equation? You can't say 2x plus x is 7. Right, because this is not equal to 2x. This is not equal to x. It's equal to the greatest integer less than or equal to x. So what we have to do is, well, so let x be a solution to this equation. Okay, the first thing I want to do is to find out which two integers is it in between for me to make this calculation. So we don't know what it is. We'll say let a be such that x lies between a and a plus 1. You want to see which two consecutive integers it lies between. And the x could be equal to this, but it's not equal to this. So if x is like here, right? X is equal to 4, so it can be equal to this. But x can't be equal to the next one, the one which is higher. All right. So this means that that is equal to a. So this part here is equal to a. It's not a square bracket, it's half a bracket like that. That's the greatest integer less than or equal to. There is a symbol, that one means the one next to it, the higher one. Right? But that's another story. Now, so how do we work out 2x now? So this is okay. So to work out 2x, if x lies between a and a plus 1, then 2a is less than or equal to 2x is less than 2a plus 2. Now you got, these are separated by two integers, and that's not going to help because I can't say what the greatest integer smaller than this is. It could be, 2a plus 1, which is beyond that. So let's separate this two cases. If a is less than or equal to x less than a plus half, let's take a plus half, because that way I'll get 2a plus 1. Then you've got 2x, 2a is less than or equal to 2x, less than 2a plus 1. Right. So in this case, you have that the greatest integer is now 2a in this case. Right. If x, okay, if x lies between a plus half and a plus 1. So x could be halfway in between. It could be on the right half or the left half. Now this is the right half. When it's between is beyond a plus half, but less than a plus 1, right? Then what happens to 2x? Then you got 2a plus 1 is less than or equal to 2x is less than 2a plus 2. Now, these are consecutive integers here. So in this case, 2x is equal to 2a plus 1. Right. Now, let's take this case here. If x is this, then this equation here, let's okay, I think I can squeeze this in. Now you got 2x plus x equals 7 implies that, let's take this case here. Now in this case, 2x is equal to 2a, and x is always equal to a, and that is 7, and that implies that 3a is equal to 7. But a is an integer, you see. Right? A is an integer. This a is chosen to be the greatest integer smaller than a. And this, when you solve for a here, you don't get an integer, you get 2 1/3. So this cannot be. This is, x cannot lie like this. This is impossible. Because if x is satisfied this condition, you get an impossible situation. And we said x is a solution. But in the other case, in this case, what do you have? You have that that implies, now this 2x here, in this case here, was 2a plus 1. And you have, that is a. So now you have 3a plus 1 is equal to 7, and you get a is equal to 2. So you do have a solution. A is equal to 2, right? And x will then lie. We are taking this case here. There's no solution there, but there is a solution here, right? And a is equal to 2. So if you put a equal to 2, you will see that 2.5 is less than or equal to x, less than 2 plus 1 is 3. So the solution to this is, there are many, many solutions. All these numbers will satisfy this equation. X lies between 2.5 and 3, right? Now, if you want to try it out, for instance, let's clear everything. So we said x lies between 2.5 and 3. Let's take, for instance, let x be equal to 2.7, for instance, right? That's the number which lies between 2.5 and 3. Then you got the greatest integer, 2x is 5,4 plus 2,7. Now the greatest integer here is 5, right? And here it's 2. There it is, 2,7 satisfies this equation. In fact, if you put any number between 2.5 and 3, it will satisfy this equation, and no other number will satisfy it. And we have did the mathematics to prove that. Okay,